Okay, let's move on. I think the tutorial after we do the set surveying, and then we need to like see how we can obtain that optimal structure using the MATLAB code together with Abacus. So this is the general like a reference to the lecture notes. I hope you have already watched the lecture recordings online on Canvas. And then this is the major, you can review it. Roughly the idea is that we convert it from 3D to a 2D problem, divide it into elements, and then using MATLAB to get the 2D output, and then we use the 2D graph to form a 3D object in Abacus. So let's see, the first thing I think we get, as I mentioned, we get a 2D design domain from 3D. We neglected the thickness, so we get the length along x is 400 millimeter, overall height is 400 millimeter as well. Let's see, next step we are going to divide the whole design domain into element. So let's consider we will choose an element size of 10 millimeter times 10 millimeter, a square. And then in theory, we can divide the whole design domain into 40 elements along X, 40 elements along Y. So this will form the input parameter uh, that we are going to use the optimization tool, which is this code. This code. If I enlarge it, we call it BSO2DC.m. So in the bracket, that will be the input parameter that you are going to use to you obtain from that design problem. Actually, the inbuilt a structure problem is fixed at the left end, and then there's a point load acting on the top right point on your model. So this will be the structure analysis problem idealized to 2D. Next one, we need to consider what's the possibly each input parameter means. So there are 6 parameters. So the first one indicate I listed here. You can have a look. But the first one will be the how many elements along X, how many elements along Y. We know it's 40 and 40 if we use the element size of 10 millimeter. And then G bar is the volume fraction. We will tell how many elements will be kept after the optimization. So roughly we use the remaining elements divided by the total element there. Uh, the epsilon and then beta, they are controlling how many elements will be removed. This one is how many elements will be removed in each iteration. Um, if we divide it by, it's a fraction, which use the element to be removed in each iteration by the total element in the design domain. Beta is similar meaning, but it's just a little bit more. Remember, BSO means bidirectional. We can remove elements. If it's not efficient, we can add elements if it is efficient. So the beta representing how many elements will be removed and will be added in each iteration. So roughly the beta should be larger than epsilon. So for epsilon, there's a default value of 0.01, 1%. Beta is 0.05, that's 5%. The last parameter uh, is define the minimum sizes in your optimal structure. So I will explain a little bit more using the optimal topology we obtain. So we move on. So based on this, we can gathering an input for our problem. This supporting bracket. Um, we can get is a 40-40. If we actually want to uh, intend to use material usage, which is a 4.4 times 4 million millimeter cubic meter. And then the initial design domain we get is actually 8 times 10 to the power 6, 8 million millimeter cubic. And then we can get is using this value divided by the design domain, approximate design domain size, which is we get 0.5. So we set at 0.5. Roughly, that's if the whole design domain have 100 elements, you are going to remove 50% of it, 50 elements. And then this two parameter default. Lastly is the for. I will explain a little bit more using for later on. So we just copy this one and then to run this command in the MATLAB. So just open MATLAB. So when you open MATLAB, that should be the default interface. So the first thing we need to build a virtual space that's to host all the files we are going to use. Similarly, you make a folder. um, okay, make a folder. I'm going to direct it to my folder like teaching, probably this one, and then make this year, and then tutorial number 1. I will choose this one. So when I enter this folder, I think that's my tutorial notes and then some graphs there. So what we want to find is this file beso2dc.m. If you haven't have this file, please download it from the canvas under tutorial 1 learning materials. You can find this file, and then if you double click this one, and then we'll enter into, you see, directly switch from home to the editor. So before I move to run the command, I want to give you a brief introduction to the MATLAB interface. I suppose you should complete this course in your year 1 courses. So just for you to get a review, very simple. For any like program, you will have like a quick access bar here, some um, like tapes over on the top, which guide you for different sets of quick access buttons, different functions there. So in here will be your current working folder, current folder. So only your code will be placed in this current working folder, then you can run it accurately. So if you can't see it under your working folder, I think if you run it, you will get some error. In here, it will be the editor window. That will be the MATLAB code for this small tool BSO2DC. And then here we call it, this one is a command window. For the command window, we can like paste the comments we copied from our tutorial notes here, and then we can run it. And then the workspace, when you run it, you will notice there is some variables you are use, and then you can check the corresponding values. I think if you debug or change the code, it may be helpful. The other thing is the functions that are available inside of your code. Roughly, you can use like a TOBS101 directly to replace the BSO2D code. They're the same. So you can use either the file name as the command line or the functions as the command line. So now let's see how we run it. So after we run it, and then yeah, you can see this will be the text output. And then later on, a window will pop up to show you the graphical output. And then the program will run iteration after iteration to remove, I think, 1% of the total elements. And then we will check the performance. We call it complaints, mean complaints, and then also check the volume. So check the objectives and then constraints. When the error is less than like 0.1%, which lasts for at least 5 or 4 iterations, we will consider we obtain an optimal solution. So this is the graphical output. This is the text output. Actually, you can copy this one because this one will tell you how many iterations you use to obtain your current optimal design, and then what's the mean complaints. This one is objectives. I think I will explain a little bit more in future. This like value will represent um, what's the stiffness of your structure. And then this will be the volume fraction, this will be the relative error. So you can copy that to your notes, and then also save this graph to your your working folder, so that you can use it later on. Remember to change it for GPG if you we want to use it in Abacus software. So usually I will name it under CB, cantilever beam, and then there's input parameters. There's four, that's enough because the other two will be default. Uh, and then you can save it. So that's all for the MATLAB part. And then we move on to the Abacus part to make this 2D optimal design to a 3D model.